Hi, and welcome to the 35th day of Just Start Programming, the Rust programming language. And I can almost see the end of the finish line of the book, so let's push forward. And today we will learn about patterns and matching in Rust. So join me once again live in one take, no shortcuts and no secrets. So let's just start programming. All right. So the other day, I think we did the object-oriented design pattern, and I think we still have some errors in the code because we did this refactoring of the design. Let's come back to the code. Yep. So here we have state, no field state on type mutable post. Yeah, because state was commented out, so we can actually remove this as well as this one. Request, review, and approve. Okay. Previously we had post, request, review, and then post, approve. But here we have post, request, review from pending review post. Okay, because request review is now in draft post. So I don't think we need this anymore. Can comment it out. Okay, and that should compile. Let's see, main RS, post content. Content in draft post. Pending post review. Pending post review. Content. Okay, so it was saying draft post, draft post, draft post, content. No method named, content found for struct draft post. Struct draft post, implement, content is here. Draft post. What is it that we wanted to do here? Oh, did I comment out something? Okay, so this one without best review post content. This one we can comment out. What's the error here? No method name. Request review found on struct draft post in the current scope. Method not found. Method not found. Okay, so this is for post. This is for draft post. Just review. Can we copy this one? Content. Draft post content. Why did I add this one? So ideally, once you add this, post content should return blank. Okay, so it should return blank. This is draft post at text. Draft post at text. Okay, so it should be blank. We can copy this and put it here. This one. Okay, so content should return blank. Then request review. Request review. Ending review. Mm. The idea again, if you have trait state, request review, approve, content will be blank. Implement state for draft. Post request review. Pending review. Pending review post is under pending review. What was commented out? Oh. Okay. It should be this one. Why did I comment that out? Post request review. Post request review. Okay, so it's this one. And post approve. Post approve. Post approve. In draft post, we have request review. So in draft post, request review. Draft post, you need to have request review. Pending, okay, so this one became pending review post. Okay, and then post approve. Pending review post approve becomes post. Like this one, post content. Did we have it here? Post content. Post content. Okay, post content is like this. We'll just return that one. So, okay. I said draft post. Post content. So this draft post content. Post review. Sun post content. Let's run this one. Error. No method named content found for draft post. Okay, so this one has an error. Under draft post, draft post content. Draft post content new. Draft post content string new. Draft post was added when the code was refactored. Okay, so let's see. Post content. We still enable the creation of new post in the draft state using post new. And ability to add text to the post content. Text to post content. Okay. Instead of having a content method on the draft post that returns an empty string, we'll make it so draft posts don't have the content method at all. That way, if we try to get a draft post content, we'll get a compiler error telling us that the method doesn't exist. Okay, compiler error method. Yeah, it doesn't exist. So we're in the right track. Okay. As a result, it will be impossible for us to accidentally display draft post content in production because that code won't even compile. Listing 18-19 shows the definition of post struct and a draft post. Post struct and a draft post. So post struct and a draft post. And then here in post you have function new, draft post, content string new. Post new, draft post, content string new. Content string new. Okay. Then you have content, self content. Okay, content is here. This is under post. While in draft post, you have add text. In draft post, you have add text. Self str content push str text. Push str text. Okay. Both the post and my mouse is jumping. Both post and draft post structs have a private content. Okay. That stores the blog post text. The structs no longer have the state field because we are moving the encoding to the state to the type of structs. The post struct will represent a published post. And it has content method that returns content. Where's the published post? Will represent a published post. The post will represent a published post. We still have post new function, but instead of returning instance of post, it returns instance of draft post. Because content is private and there aren't any functions that return post, it is not possible to create an instance of post right now. Draft post struct has an add text method, so we can add text to content. Add text. In main, add text, because post is draft post. But note that draft post does not have a content method defined. Yeah, so it will not compile because draft post doesn't have content method defined. So now the program ensures all posts starts as draft posts. And draft posts don't have their content available for display. Any attempt to get around these constraints will result in a compiler. Implementing transitions as transforming into different types. Okay, so draft post, request review, pending review post. Yeah, so draft post request review will return pending review post. pending review post. So this one will not compile because I don't have content. Pending review post content string and pending review post approve. Pending review post content approve content sub content. Okay. Just review and approve methods takes ownership of self, thus assuming the draft post and pending review post instances and transforming them into a pending review post and published post, respectively. This way, we won't have any lingering draft post instances after we call request review. The pending review post draft doesn't have content. Okay. Yeah, content as in content method defined on it. So attempting to read its content results in compiler error, as with draft post. So that's why draft post doesn't have content. So this one, if we read it, you will have compiler error. So that's why I commented it out. Because the only way to get published post instance that does have the content method defined is to call approve method on pending review post. So pending review post approve. Okay. And the approve create a post content self content. Yeah. But we also have to make small changes to main. The request review and approve methods return new instances rather than modifying the struct they're called on. So we need to add let post shadowing assignments. Let post mut post post new add text. Yeah, so we can't have the assertions about the draft and pending review post contents be empty strings, nor do we need them. We can compile code that tries to use the content of posts in those states any longer. Okay, so the updated code in main is shown here. Okay, so I think we have fixed the issues. It's mainly we commented this out. Yeah, this one is not needed at all. Okay, so that will compile the code and let's run it. Assert equal. Okay, so no issues. Alright, so that will close this chapter, object-oriented design in Rust. Now we move on to patterns and matching. So what do we have in patterns? Patterns and matching. Patterns are a special syntax in Rust for matching against a structure of types, both complex and simple. Using patterns in conjunction with match expressions and other constructs gives you more control over a program's control flow. Pattern consists of some combination of the following: literals, destructured arrays, enums, structs or tuples, variables, wildcards, placeholders. Some example patterns include X. Okay, you have the tuple here and also structs. Option is a struct or option is an enum. Struct or enum. Let's see. Where was it? Guessing game. Guessing game. I think in guessing game we have, this is where the match was introduced. Yeah, here, match. Match. Okay, error. Yeah, so this is where we first encountered match. But going back to options. Let's search here, it's easier. Rust option. STD option. Some or none. Option is an enum. Okay, so that confirms it. How about result? Result. STD result. Result is also an enum. Okay, error. Some or none option. It's an enum. Well, result is also an enum. Okay, and error. That's what's there. These two so far. Okay, so let's move on. Let's come back to this one. In the context in which patterns are valid, these components describe the shape of data. Our program then matches values against these patterns to determine whether it has the correct shape of data to continue running a particular piece of code. To use a pattern, we compare it to some value. If the pattern matches the value, we use the value parts in our code. Recall the match expression in chapter 6 that use patterns such as point sorting machine example. If the value fits the shape of the pattern, you can use the name pieces. If it doesn't, the code associated with the pattern run. This chapter is a reference on all things related to patterns. All things related to patterns. You'll cover the valid places to use patterns, the difference between refutable and irrefutable patterns, and the different kinds of pattern syntax that you might see. By the end of the chapter, you'll know how to use patterns to express many concepts in a clear way. Okay. All the places patterns can be used. Patterns pop up in a number of places in Rust, and you've been using them a lot without realizing it. This section discusses all the places where patterns are valid. Match. Okay, so here match arms. As discussed in chapter 6, we use patterns in the arms of match expressions. Formally, match expressions are defined as keyword match, a value to match on, and one of the match arms that consists of a pattern, and an expression to run if the value matches that arm's pattern. Like this, value pattern expression. For example, here's the match expression from listing 6-5 that matches on option day32. Value in the variable x. So none, none, sum, sum. The patterns in this match expression are the none and sum to the left of each arrow. One requirement for a match expression is that they need to be exhaustive. So exhaustive. So just like for option, it needs to match none and sum. Either none or sum. Exhaustive in the sense that all possibilities for the value in the match expression must be accounted for. One way to ensure you've covered every possibility is to have a catch-all pattern. For the last arm, for example, a variable name matching any value can never fail and thus covers every remaining case. The particular pattern underscore will match anything. Sounds like the default. But it never binds to a variable, so it's often used in the last match arm. The underscore pattern can be useful when you want to ignore any value not specified. For example, we'll cover the underscore pattern in more detail in ignoring values in a pattern later in this chapter. Conditional if-let state expressions. Chapter 6, we discuss how to use if-let expressions, mainly as a shorter way to write the equivalent of a match that only matches one case. Optionally, if-let can have a corresponding else containing code to run if the pattern in the if-let doesn't match. Else. So if else, but in this case there's let. Listing 19-1 shows that it's also possible to mix and match. If let, else if let expressions. Doing so gives us more flexibility than a match expression, in which we can express only one value to compare with the patterns. Also, Rust doesn't require that the conditions in the series of if-let, if-let arms relate to each other. Okay, encoding 19-1 determines what color to make your background based on a series of checks for several conditions. For this example, we've created variables with hard-coded values that a real program might receive from user input. Okay, so let's see main let favorite color, an option which is set to none. Is Thursday false? Age 34 dot parse, which is result. If let's some color, favorite color, favorite color is none, so it will not print this. Else if is Tuesday, it will not print this because it's also false. Else if let okay age equals to age. Okay. If age is greater than 30, okay, so age here is 34. So this one will print. Else, using blue as the background color. Okay. If the user specifies a favorite color, that color is used as the background. In this case, at first it's none, but if the user specifies a favorite color. If no favorite color is specified, then today is Tuesday, and today is Tuesday is green. Background color is green. Background color is green. Let's see, Tuesday. Okay, none is Tuesday. Okay, none. And today is Tuesday, so it means that Tuesday becomes true. The background color is green. Otherwise, if the user specifies their age as a string, and you can parse it as a number successfully, the color is either purple or orange. Oh, wait, purple or orange, yeah. Depending on the value of the number. If none of these conditions apply, background color is blue. Background color is blue. So we have else. Okay. This conditional structure lets us support complex requirements. With the hard-coded values we have here, this example will print using purple as the background color. You see that if let can also introduce new variables that shadow existing variables in the same way that match arms can. In the line if let okay age equals age, introduces a new age variable that contains the value inside the okay variable, shadowing the existing age variable. This means we need to place the if age greater than 30 condition within that block. We can combine these two conditions into if let okay age equals age and age greater than 30. So it says here we can combine these two conditions into this one. The new age we want to compare to 30 is invalid until the new scope starts with a curly bracket. The downside of using let expressions is that the compiler doesn't check for exhaustiveness, whereas match expression does. It does. If we omitted the last else block and therefore missed handling some cases, compiler will not alert us to the possible logic bug. Omitting the last else block. So it says the compiler will not alert us. Okay. While let conditional loops, similar to if let, the while let conditional loop allows a while loop to run for as long as the pattern continues to match. In this thing 19-2, we show a while let loop that waits on messages sent between threads, but in this case checking a result instead of an option. So we have channel, thread spawn, sending val 123, while let OK, rx receive, print line the value. So this one, while loop to run for as long as pattern continues to match. Okay, how about for loops? In a for loop, the value that directly follows the keyword for is a pattern. For example, in for x in y, in x, the x is the pattern. Listing 19-3 demonstrate how to use a pattern in a for loop to destructure or break apart a tuple as part of the loop. So if you have this, enumerate. Okay, so you're getting a tuple of index and value. The code in 19-3 will print the following. Okay. We adapt an iterator using enumerate method, so it produces a value. It produces a value and the index for that value placed into a tuple. The first value produced is the tuple 0, 8. When this value matches to the pattern index value, index will be 0 and value will be 8, printing the first line of the output. Okay. How about let statements? Prior to this chapter, we had only explicitly discussed using patterns with match and if let. But in fact, we've used patterns in other places as well, including let statements. For example, consider this straightforward variable assignment with let. Every time you've used a let statement like this, you've been using patterns. Although you might not have realized it, more formally, a let statement looks like this. Let pattern equals expression. In statements like let x equals 5 with variable name in the pattern slot, variable name is just a particularly simple form of a pattern. Rust compares the expression against the pattern and assigns any names it finds. So in the let x equals 5 example, x is a pattern. That means bind what matches here to the variable x. Because the name x is the whole pattern, this pattern effectively means bind everything to the variable x, whatever the value is. To see the pattern matching aspect of let more clearly, consider listing 19-4, which is a pattern with let to destructure a tuple. XYZ 1, 2, 3. Here we matched a tuple against a pattern. Rust compares the value 1, 2, 3 to the pattern XYZ and sees that the value matches the pattern. In that the number of elements is the same in both Rust. So bind 1 to X, 2 to Y, and 3 to Z. You can think of this tuple pattern as nesting 3 individual variable patterns inside it. One moment. You can think of this tuple pattern as nesting three individual variable patterns inside it. If the number of elements in the pattern doesn't match the number of elements in the tuple, the overall type won't match and we'll get a compiler error. For example, in 19-5 shows an attempt to destructure a tuple with three elements into two variables, which won't work. Okay, so here you have 1, 2, 3, but you are getting x and y, so let's see, it will complain. Expected a tuple with three elements, found one with two elements. To fix this error, we could ignore one or more of the values in the tuple using, this is something new, underscore or dot dot, as you'll see in ignoring values in a pattern section. If the problem is that we have too many variables in the pattern, the solution is to make the types match by removing variables, so the number of variables equals the number of elements in the tuple. Function parameters. Function parameters can also be patterns. In the code listing 19-6, which declares a function named foo that takes one parameter named x of type i32 should by now look familiar. The x part is a pattern. As we did with let, we could match a tuple in a function's arguments to the pattern. Listing 19-7 splits the values in a tuple as we pass it to a function. Okay, so this one is a reference to a tuple. Okay, so you're borrowing 3 and 5, point equals point and point is added here as a reference, and then print coordinates. So it will print x and y. So 3 and 5 will be printed out. Will it run? Okay. 3, 5. This code prints current location 3 and 5, the values ampersand 3, 5 matches the pattern ampersand x, y. Here. So x is the value 3 and y is the value 5. You can also use patterns in closure parameter list in the same way as in function parameter list, because closures are similar to functions as discussed in chapter 13. At this point, you have seen several ways to use patterns, but patterns don't work the same in every place we can use them. In some places, the patterns must be irrefutable. In other circumstances, they can be refutable. We'll discuss these two concepts next. Okay, so irrefutable and refutable. Refutability, whether a pattern might fail to match. Patterns come in two forms, refutable and irrefutable. Patterns that will match for any possible value passed are irrefutable. So, will match for any possible value, irrefutable. An example would be x in the statement let x equals 5, because x matches anything, therefore cannot fail to match. Patterns that can fail to match or for some possible value are refutable. An example would be sum x in the expression if let sum x equals a value, because if the value in a value variable is none rather than sum, the sum pattern will not match. refutable. Function parameters. First, function parameters, let statements and for loops can only accept irrefutable patterns because the program cannot do anything meaningful when the value don't match. The if let and while let expressions and then let else statement accept refutable and irrefutable patterns. So the compiler warns against irrefutable patterns because by definition they're intended to handle possible future failure. The functionality of a conditional is in its ability to perform differently depending on success or failure. In general, you shouldn't have to worry about distinction between refutable and irrefutable patterns. However, you need to be familiar with the concept of refutability so you can respond when you see it in error messages. In those cases, you'll need to change either the pattern or the construct you're using the pattern with, depending on the intended behavior code. Let's look at an example of what happens when we try to use a refutable pattern where Rust requires an irrefutable pattern and vice versa. So listing 19-8 shows that statement, but for the pattern, it specified some irrefutable pattern. As you might expect, this code will not compile. If some option value were a non value, it would fail to match the pattern, meaning the pattern is refutable. However, the last statement can only accept an irrefutable pattern because there's nothing valid in the code can do with a non-value. At compile time, Rust will complain that we've tried to use a refutable pattern where an irrefutable pattern is required. Some optional pattern none not covered. Let bindings require an irrefutable pattern. Because this one is refutable. Okay, because we didn't cover and couldn't cover every valid value with the pattern sum, Rust rightfully produces a compile error. If we have a refutable pattern where an irrefutable pattern is needed, can fix it by changing the code that uses the pattern. Instead of using let, we can use if let. Then if the pattern doesn't match, the code will just skip. Okay. Let's sum option else return. Okay, so using let else and a block with refutable patterns instead of let. We've given the code an out. This code is perfectly valid now. However, if we give if let an irrefutable pattern, a pattern that will always match, such as x as shown in 19-10, the compiler will give a warning. This one will always match. Let's see if we run this. No auto. Rust complains that this doesn't make sense to use if let with an irrefutable pattern. Okay, so that is let x equals to 5. For this reason, match arms must use refutable patterns. Match arms, refutable patterns. Except for the last arm, which should match any remaining values with an irrefutable pattern. Rust allows us to use an irrefutable pattern in a match with only one arm. This syntax isn't particularly useful and could be replaced with a simpler let statement. Now that you know where to use patterns and the difference between refutable and irrefutable patterns, let's cover all the syntax you can use to create patterns. Pattern syntax. Oh, it's a long one. Okay, so this is informative. Pattern syntax. In this section, we gather all the syntax that is valid in patterns and discuss why and when you might want to use each one. So matching literals. What do we have here? Okay, so we have 1, x, 1. Okay, so depending on the number. And anything else beyond 1, 2, and 3 will be handled by this underscore. The code prints 1 because the value in x is 1. Okay. Matching named variables. Named variables are irrefutable patterns that match any value, and we've used them many times in this book. However, there is a complication when you use named variables match if let or while let expressions, because each of these kinds of expressions starts a new scope, variables declared as part of a pattern inside the expression will shadow those with the same name outside, as in the case with all variables. 19-11, we declare a variable named x, the value sum, which is 5, the variable y, the value 10. When we create a match expression on the value x, match expression value x, look at the patterns in the match arms and print line at the end. Try to figure out what the code will print before running this code or reading further. Okay, let's try to see. Sum is 5. Match x. X is sum 5. So this one will not print. This one will not print. Okay, so this one will handle all cases. So it will be sum 5. Right. Let's walk through what happens when the match expression runs. The pattern in the first match arm doesn't match the defined value x, so the code continues. Pattern in the second match arm introduces a new variable y that will match any value inside a sum. Because we're in a new scope index inside the match expression, this is a new y variable, not the y. We declare beginning with the value of 10. This new y binding will match any value inside a sum, which is what we have in x. Therefore, this new y binds to the inner value of sum. Sum in x. That value is 5, so the expression for that term executes and prints match y equals to 5. Match y equals to 5. If x had been none, the value instead of sum, the patterns in the first two arms wouldn't have matched. So the value would have matched to the underscore. Okay. X is none, this one will not match. and it will consider the underscore. Okay. When the match expression is done, its scope ends, and so does the scope of the inner y. The last print line produces at the end x equals y equals 10. Okay, to create a match expression that compares the values of outer x and y rather than introducing a new variable that shadows an existing y variable, we would need to use a match guard conditional instead. Talk about match guards later in extra conditionals with match guards. Okay, multiple patterns. You can match multiple patterns using pipe syntax, which is the pattern or operator. For example, in the following code, we match the value of x against match arms, the first of which has and or, meaning the value of x matches either the values in the arm that's arm's code run. Okay, so there's this. So is it or? Okay, so it's or. 1 or 2. Okay. Matching ranges of values with dot dot equals. Okay, so this is also something new. Dot dot equals. Syntax allows us to match an inclusive. Oh, that's why we have this one before. Dot dot equals. Inclusive range of values. In the following code, when a pattern matches any of the values within a given range, that arm will execute. Okay. If x is 1, 2, 3, 4, 5, first arm will match. This syntax is more convenient for multiple match values than using the pipe operator to express the same idea. If you were to use, okay, let's call this or, you would have to specify 1 or 2 or 3 or 4 or 5. Specifying a range is much shorter. Okay, so an option for this is this one. Or an option for this, which is quite long, is this one, shortened version. Okay. The compiler checks the range is an empty at compile time, and because the only types for which Rust can tell Rust is empty or not are char and numeric values. Ranges are only allowed with numeric or char values. Here's an example of using ranges of char values. Okay. Dot equals. Rust can tell that C is within the first pattern's range and prints early as ASCII later. Destructuring to break apart values. You can also use patterns to destructure structs, enums, tuples, to use different parts of these values. Let's walk through each value. Destructuring structs. Okay, what do we see here? No point x and y. So point x is 0 and 7, you get p, which is point. Then point P is, okay, so now point P looks like a parameter here for point. Okay, this code creates the variables A and B, A and B. that matches the values of x and y fields of the struct. This example shows that the names of the variables in pattern don't have to match the field names of the struct. However, it's common to match the variable names to the field names to make it easier to remember which variables came from which fields. Because of this common usage and because writing lat point contains a lot of duplication, Rust has shorthand for patterns that match struct fields. You only need to list the name of the struct field and the variables created from the pattern that have the same names. Okay. Let's see. X and Y. So X and Y to P. P is binded to this one. This one is also interesting. We can also destructure with literal values as part of struct pattern rather than creating variables for all the fields. Doing so allows us to test some of the fields for particular values while creating variables with structure to other fields. Okay, let's see here. Expression separates point values into three cases. Points that directly lie on x, which is true when y equals 0, on y, x. Okay, so this one is already using struct field. Okay, so it says that's the note again. Okay, so the pattern don't have to match the field names of the struct. However, it's common to match the variable names to the field names to make it easier to remember which variables came from which. So it can look like this also. Xy equals to 0, x 0, y. Okay. So this one is the explanation to this. So since you have 0 and 7, first arm will match any point that lies on x-axis, specifying y. Field matches if its value matches the literal 0. Pattern still creates x variable that we can use in the code for this arm. Similarly, the second arm matches any point on the y-axis by specifying that the x field matches its value is 0 and creates a variable y for the value of y field. The third arm doesn't specify any literals, so it matches any other point. So instead of underscore for structs, it can look like this also. Okay, destructuring enums. We've destructured enums in this book, for example 6-5, but we haven't yet explicitly discussed that the pattern to destructure an enum corresponds to the way the data stored in the enum is defined. As an example, in listing 19-5, we use the message enum from listing 6-2 and write a match with parameters that will destructure each inner value. Message as an enum, quit, move, write, change color. Okay, so if the message is quit, you'll do this. Okay, so message move x and y. Message write text. Change color. Okay. Code will print change color to red 0, green 160, and blue 255. Try changing the value of the message to see the code from the other arms. Change color to red, change color, so it was calling this part. Green 160 and blue 255. Value of the message. For enum variants without any data like message quit, then can't destructure the value any further. We can only match the literal message quit value and no variables are in that pattern. We have message move. We can use a pattern similar to the pattern we specify to match structs. Okay, after the variant name. Like message write that holds a tuple with one element. Message color, change color that holds a tuple with 3 elements. Pattern is similar to the pattern we specify to match tuples. Okay. Destructuring nested structs and enums. Nested structs. So far, examples have all been matching structs or enums in one level deep. Matching can work on nested items too. For example, you can refactor the code to support RGB and HSV colors in change color. So color, RGB, HSV. Let message change color. Message change color. Okay. Color RGB. Color HSV. Okay, so the pattern of the first arm in the match expression matches message change color. Enum variant contains a color RGB variant. But this is HSV, so it will print this part. Okay, destructuring structs and tuplets. We can mix, match, and nest destructuring patterns in even more complex ways. The following example shows a complicated destructure where we nest structs and tuples inside a tuple and destructure all the primitive values out. This code let us break complex types into their component parts so we can use the values we're interested in separately. Destructuring with pattern is a convenient way to use pieces of value such as the value from each field in a struct separately from each other. Okay, ignoring values in a pattern. You've seen that sometimes it's useful to ignore values in a pattern, such as the last arm of match, to get a catch-all that doesn't actually do anything, but does account for all remaining possible values. A few ways to ignore entire values or parts of values in a pattern using the underscore pattern, which you've seen, the underscore pattern with another pattern using a name that starts with an underscore, using dot dot to ignore remaining parts of a value. Let's explore on how and why to use each of these patterns. Okay, an entire value with underscore. We've Use the underscore as a wildcard pattern that will match any value, not bind to the value. This is especially useful when the last arm is match expression, but you can also use it in any pattern, including function parameters as shown. Okay, so underscore can be here. This code will completely ignore the value 3 passed as the first argument and will print this code only uses the y parameter. Okay, in most cases, when you no longer need a particular function parameter, you will change the signature so it doesn't include the unused parameter. Ignoring a function parameter can be especially useful in cases when, for example, you're implementing a trait when you need a certain type signature, but the function body in your implementation doesn't need one of the parameters. You then avoid getting a compiler warning about unused function parameters as you would if you used a name instead. Parts of a value with a nested underscore. We can also use underscore inside another pattern to ignore just part of a value. For example, when we want to test only part of a value but have no use for other parts in corresponding code to run. Okay. So, this code responsible for managing a settings value. Managing a settings value. The business requirements are that the user should not be allowed to override an existing customization of a setting, but can unset the setting and give it a value if it is currently unset. Okay, so here you have some mutable setting value, some new. Okay, match setting value, new setting value. Some underscore. Okay, so this is like a tuple. Some underscore and some underscore. Ah, this is interesting. Okay. Can override an existing customized value. Any of underscore setting value equals to new value. This code will print can't overwrite an existing customized value, and then setting is sum 5. Okay, it's referring to setting value. In the first match arm, we don't need to match on or use the values inside either sum variant, but we do need to test for cases when setting value and new setting value are sum variant. In that case, we print the reason for not changing setting value and it doesn't get changed. In other cases, if either setting value or new setting value is none, expressed by the pattern in the second arm, okay, we can also use underscores in multiple places. Oh, you can put underscore here. First, okay, then here it could be anything. Third, fifth. Ignoring multiple parts of a tuple. This code will print some numbers to 832. Okay, this one is for 832. about unused variable by starting its name with underscore? Okay, so I think we have seen this before. If you create a variable but doesn't use it anymore, Rust will usually issue a warning because an unused variable could be a bug. However, sometimes it's useful to be able to create a variable you won't use yet, such as when you're prototyping or just starting a project. In this situation, you can tell Rust not to warn you about the unused variable by starting the name of the variable with underscore. Okay, so that's how you do it. So it's like a placeholder. Okay, so Y will get a warning, but you will not get a warning with underscore. Underscore. Okay. Syntax underscore x still binds a value to the variable, whereas underscore doesn't bind at all. Okay, this one will have an error. It's error. Unused variable. Okay, we receive an error because s value will be moved into underscore s. Move to underscore s, which prevents us from using a again. No, not a, s. However, using the underscore by itself doesn't ever bind to the value. Okay, so underscore is here. This code works just fine as you never bind s to anything. It isn't moved. Okay. Remaining parts of the value with dot dot. Oh, you can also, okay, so for the benefit of time, maybe let's just go through and see that is here. So dot dot ignores any parts of value that we haven't explicitly matched the rest of the pattern. Okay, so here you have dot dot x and then dot dot. Okay, so in this case, first dot dot and last. However, using dot dot must be unambiguous. If it's unclear which values are intended for matching and which should be ignored, Rust will give us an error. Okay, so this one will not compile. How do we know second is supposed to be this? Okay, so what else is here? Extra conditionals with match guard. Okay, so match guard is an additional if condition specified after the pattern in a match. Okay, so if is here. Match guard. So you can put in if statements. There's no way to express if x modulo 2 equals 0 condition with a pattern, so the match guard gives us the ability to express this logic. The downside of this additional expressiveness is that the compiler doesn't try to check exhaustiveness when match guard expression are involved. Using a match guard to test for equality with an outer variable. If n equals y, sum n. Okay. If n equals y is not a pattern and therefore doesn't introduce new variables. See up here. I can have this, and then you have if y, and if y is true, okay, because y here is like a boolean. At bindings, that operator lets us create a variable that holds a value. At the same time, we're testing that value for a pattern match. Okay, so I think we can use this pattern syntax as a reference later on. We'll be using all of them. Okay, so let's end here, and thank you so much for joining me today. And before we finally end, let me thank my supporters.